There we go. There's Earl, there's Ashley, and let me move to the do now, do now. All right, 2 do nows. Let's give you 2 minutes. 2 minutes. I was singing to Alosa. You guys got here early. You could have heard me singing to Alosa. And this is beaker 1, 2, 3, 4, and 5. One of you guys asked which, well, I don't see numbers for the beakers. Well, let's just do an order. 1, 2, 3, 4, 5. Kind of a review of what we've done in the past, and we'll get back to surface area to volume ratio. So which one of these beakers is hypertonic to the bag inside? And if you do, or if you are taking the retake today for the quiz, I do have to be with freshmen today at 3 o'clock. So I'll open the quiz at 3, even though I will not be there. You can find it under the same place that you found the lesson before, which can be passive and active transport. That'll be it. And then the second question here, though, is which will experience the highest rate of osmosis? Highest rate. So if you're going to measure rate. So let's see. It is approaching 2 minutes. We're almost there. We're almost there. Send me your, go ahead and give me your answers in the chat. I'm not going to tell you guys what hypertonic means. That's for you. I taught that before. You're supposed to be studying. So no hats from me.
Mr. Pope, do you mean
yes.
Which bag out of the hypertonic solutions or which bag out of all of them?
For the second question or the first question?
The second question.
Yeah, which bag out of all of them? There's only one answer for the second one. There's So drop your answers in the chat. Drop your answers in the chat.
Oh.
Okay, so let's take a look at the answers now. Time is up, so let's see what we've got. I have a bag that has 2 moles of whatever the solute is. I've got 2 moles in all these bags. No, I don't. I've got 1 mole in this particular bag. So 2 moles, 2 moles, 2 moles, 1 mole, and 2 moles in the contents of the bag. There are 6 moles in this solution. So this solution is greater, has more solutes, less water than the bag, therefore it's hypertonic. So 1 is hypertonic. This one is not. It's going to be hypotonic. This one's hyper, so that can't be it. So it's not 1 and 2. So that's going to get rid of C. 5, because a lot of you guys were telling me C. 5 is hypertonic. I've got 0.4 moles, 0.2 moles. So this has got more solutes than water. So 5 would maybe be hypertonic as well, but 2, we're going to get rid of C right off the bat. I know that can't be an answer. I know 1 is, let's go to the 3rd one. So the 3rd one is isotonic. So then let's go to the 4th one. 4th one is hypertonic and the 5th one is hypertonic. So 2 and 4, 3 and 4. So 3 and 4 can't be an answer because 3 and 4, this one's isotonic. So the only answer that fits in this case is D, 4. This one is hypertonic compared to this. Other ones are as well, but the solution is hypertonic to the bag. And so the only answer that fits would be D. You would, even though there's other possibilities for being hypertonic, there's only one answer choice that actually fits, and that would be D. Let's go to number 2.
Could you explain that again?
Well, so this one's hypertonic. So 1, 4, and 5 are all hypertonic solutions, but I don't have 1, 4, and 5 as options. That doesn't give me options. So I just got to go and look for the ones that have that option, option that fits. So beaker 3 is isotonic. That can't be an answer. Strike it. Beaker 2 and 4. This one's hypotonic, so I can't use that one. So B is not an answer. One's hypertonic, but 2 is hypotonic, so that can't be an answer. So I strike C. 4. Beaker 4 for D is hypertonic, so that is a check. Answer choice E, this one is going to be isotonic, not beaker 3, and this one's hypertonic, so that can't be an answer. The only answer that actually makes any sense is going to be D, beaker 4 is hypertonic to that bag, that little bag. So then we want to get to the second part of the question about rate. How fast is this going to occur? How fast is this going to occur? Well, the difference in concentration gradient is going to tell me which one's going to happen fastest. So which bag will experience the fastest rate of osmosis? So which is concentration gradient is greater? Which of these solutions is the biggest difference between them? Well, 0.2 and 0.6 is 0.4, so that's going to be 0.4. That's a possibility. 0.2 and 0.1. That's a difference of 0.1. That's greater than that, so that's not going to work. 0.2 and 0.2, there's no difference. 0.2, no, 1 and 0.2. Whoa, that's a big difference there. That is actually 0.8 difference. That's 1 whole mole, not 0.1 moles. That's 1 whole mole. Yes?
Is beaker 2 also 1?
Oh my God, you're so right. Hold on a second. You are right. That's 1 mole in the solution. And remember, I told you, anybody that corrected me today gets 5 points on the next quiz. So, boom, you got it, Abby.
What about Alosa for last time?
Oh my God, Alosa, oh my gosh, what am I going to do? Let's see if there might be some more chances today. So this is 0.1, so that actually makes sense then. So this 2 and 4 are hypertonic. I didn't even see that. Good eye. That's 1 mole, not 0.1 moles. Good eye. So actually, I guess our answer is actually B in the first chance, in the first example. This is B is our answer. Good eye, Abby. I did not see that. This is 1 mole and that's 1 mole. That's, I got confused by the blue. I'll blame it on that. That's not true. I just wasn't paying attention. But you're right. So this is going to get, well, which one has the greatest difference? Well, in this case, 0.2 and 1, that's going to be a difference of 0.8. And this one is also a difference of 0.8. So this is going to be both 2 and 4 again. They have the biggest difference between the two. And that is going to make sure that in this case, beaker 2 and beaker 4, since they have the greatest difference, they're going, it's like a hill. Your gradient, the slope of your line is going to be greater. Therefore, the rate is going to be faster in 2 and 4. So good job. Yeah. Okay, so we're going to move back to surface area to volume ratios. I'm going to do the first 2, and then you guys are going to do the others. You guys are going to do the others. So let me look at the formula here. We're going to use the formula for the surface area of a cube. So there's a formula here. So length times width times 6. So surface is going to be length times width times 6. My dimension is over here, or at least my length of one side is over here. It's 1. So 1 times 6 is going to be pretty straightforward. It's going to be 6. Over here, I see volume is length times width times height. That's going to be 1 times 1 times 1. So that will be 1. Now, how I do this, the ratio, and you have to be very careful. In a moment, I'm going to give these all to you, and I'm going to come and ask you for these numbers, and you're going to have to give me these numbers. Now, you guys wrote this down last time. So I'll do the next one, and then you need to get yours out, the one that you wrote. You copied this table down, and then you're going to be calculating these other cells, and I'll be asking you for whatever your calculation is. So to take care of the ratio, it's really straightforward. You're always going to do, I want you always to think about volume as being the denominator. So volume, we're going to say, is 1 divided by 1. So 1 divided by 1 is 1. I'm going to come over here and I'm going to divide 6. I'm going to use this as my denominator, so this is going to be my numerator. I'm going to take 6 divided by 1, which is also going to be 6. So this is 6 to 1 ratio. It's pretty easy when you've got this already converted. I'll do number 2. So I've got 2. This one's going to be 2 nanometers. So this cube is going to be slightly larger. So 2, I'm going to say 2 times 2 is 4 times 6 is 24. Easy enough. And then length times width times height. So that's all going to be 2 times 2 is 4 times 2 is going to be 8. So now we've got our calculator, our volume of our cube and the surface area of our cube. Now let's figure out the ratio. So 8 divided by 8 is going to be 1. 24 divided by 8 is going to be, how many times can 8 go into 24? Well, 3 times. So our ratio is 3 to 1. I'm going to pause for 4 minutes and let you guys calculate the rest of these, and I will call on, it looks like 8 different people to give me answers for these other rows, each one of these rows. Is there a question before I turn you guys loose to do this? Before I turn you guys loose to do this, is there a question? Yep, it is straightforward. Okay, go, 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 go. You got 4 minutes. I'll set a timer. Good to see you guys crack-a-lacking and working it out. Let's see who those persons are going to be. I see Dylan working on it. He's in the room with me. Good job, Dylan. Let's see Cam. Cam, you write it down? You wrote down this table last time. So you'll need to be making these calculations. Oh, what the heck? I just sent you a message. That's the name of the band. La 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 la, baby, goodbye. There were times when Mom would be so upset. Do, do. Remember, if somebody makes a mistake and you catch it, you get 5 extra points. You have to catch them. If somebody makes a mistake or I make a mistake, I'm just going to take their word for it, whatever they put in here. Somebody says, no, that's not correct. Well, then they will get 5 extra points on the next quiz, which will probably be Thursday. All right, that's 30 seconds to go. We've got 30 seconds. I'll call in the first person in 30 seconds. All right. Let's see who the first contestant on the Pope is Right is going to be. It's going to be our good friend, Mia Wallace. Mia Wallace. All right, let's take the first one. Mia, so what is the surface area for a cube that has 3 nanometers?
54.
54 is correct. 3 times 3 is 9 times 6 is 54. What is the volume?
27.
77?
27.
47?
27.
I'm not hearing you.
27.
27.
Alyssa, are you in the Zoom?
27.
Oh, you know how to use the Zoom classes.
Gotcha.
Wait, yes, you
All
do.
right. Thank you so much. What is my
We're getting ready
ratio?
for our test. Join the Zoom. Alyssa. I'm just saying, because I don't even know if this test is open.
Drop it in the chat.
I need you to join so we can save our.
Drop it in the chat.
It's 1.
I read a little bit.
Thank you, sweetheart. I see it. 2, 2, 1. Excellent. Good job. Good job. I'm proud of you. Your mom is proud of you. We're all proud of you. Everybody's loving it. Romello. 4-sided. Romello. Romello. I think he's in here. Better be in here. There he is. Yeah, you're here. Romello, I need you to chime in, dude. Either that, I'm going to bounce you out of here. Either drop it in the chat, or say it. Otherwise, I'm going to assume that you're not here and just bounce you out of class. Give you 15 seconds. I think he bounced himself. Coolio. Easy breezy lemon squeezy. Let's go to Ashley Medlock. Ashley.
So, 96,
6. Okay. Volume.
64,
64. Okay. And the surface area to volume ratio.
1.5 again.
Oh my gosh, good job. Let's see. Looking good, kid. Excellent, excellent, excellent. Let's go to our good friend. Who do I want to pick on? Somebody I know I can hear. Tracy, I can usually hear you pretty well. Tarleton, what you got?
Can you hear me?
I can hear you like a champion.
Okay. 150.
150. Surface area. What's the volume?
125.
125. Excellent. What's my ratio?
1 to 1.
What is it? 1 to 1?
1 to 2 to 1.
1 to 2 to 1?
Right?
Okay.
I think she means 1.2 to 1.
All right, who said that?
Earl.
Earl, you got 5 points.
Yeah.
Keep it up, keep it up. That's right. It's 1.2 to 1. There you go. Now we're cooking with Crystal. There you go. All right, thank you so much. All right, let's go to the Donalia Lopez.
Hi.
I always butcher your name. It's terrible.
216,
216,
216,
216,
1-to-1 ratio.
1 to, whoa, 1-to-1 ratio. Excellent. Thank you. I'm proud of you. Mama's proud of you. We're all proud of you. Let's go to Emma. Emma, next door neighbor. What do I have for surface area here? My calculation.
Mr. Pope, really quick, I have a question.
Okay.
So why are we doing it for 1 instead of like simplifying it?
Oh, I'll show you in just a moment. You'll see. You're jumping ahead. You're thinking this. I'll show you in just a moment. So Emma, are you there? Or do I? You can either put it in the chat or you can come
I
on.
was confused on how to do it, so.
Okay, well, now you can do it. I'll help you. So I got 7. You're just using the formula. So my side is 7. So 7, and it's a cube, right? So all sides are equal. It's a perfect cube. All sides are equal. So the length of one side is 7, and if every side's equal to one another, so it'd be 7 times 7 times 6. And then you do the same thing over for volume, 7 times 7 times 7. So we'll wait for you to give us those calculations. Hands are cold. It's like an ice box.
294 and 343.
343?
Yeah.
343. Excellent. Now, 343 divided by 343 is 1. So that's 1. What is 294 divided by 343? 294 divided by 343. What's that number? That's going to be less than 1. You're rounding up or rounding down?
Yeah.
0.9. Okay. Okay. We'll do that. I'm down with that. 0.9. Okie doke. 8. Let's go to 8. That's going to be Dylan. Dylan.
Okay, so it's 384.
384.
512.
512. So
And
what's the ratio?
I said 0.75.
Sorry?
0.75. I don't know.
0.10?
0.75.
0.75. Let's see. This is okay. I'm going to round up. Let's just say 0.8 then. 0.8. Oh my God. Okie dokie. Let's go to the next person. Let's, whoop, somebody's not happy with your answer. Let's see.
Oh no, like why is 7 like that? Like would you just
Say again.
0.9 to 1, or would you do it like where you simplify in fraction?
No, I'm just trying right now. I'm trying to keep the volume, and so the volume is going to be consistent. You're going to see. I'm going to make an analogy out of this in just a second. I'm going to use an analogy to try to get the point across of why we're even doing this in the first place. You'll see what I mean in just a sec. So let's go to Daisy Aguilar.
I got 486.
486. Okay.
729.
729. Okay. What's my rate? 0.7. 1. Okay, let's go to the last one, which is going to be, that's the easiest of them all. Let's go to Tabitha Hairball.
Sorry. Okay, so for surface area, I got 600.
Mm-hmm.
And then for volume, I got 1,000. And then
Okay,
for the ratio, I rounded up, so I did 0.6 and then the 1.
0.621. Okay. What grows faster? What increases faster? Volume or surface area? Drop it in the chat. What is increasing more quickly? Volume as I increase in size. Does volume or surface area grow more quickly? Which is it? I've got 27 people in here. So I've got 7, 8, keep it up. 10, 11, 12. That's almost everybody. Okay, keep it up. Oh, you guys are doing it, everyone. You can all see each other's answers. That makes me sad. Next time we'll keep it private. Yeah, your guys are right, though. It's not hard to notice that it is going to be volume. Volume is going to increase. It's going to be exponential. This is going to be still exponential, but it's going to be more logistical than this. So let's look at it for just a sec. So I got 1 to 8. That's an 800% increase. If I look at for volume, I'm increasing by 300%. 24 divided by 6, no, that's 400%. 24 divided by 6 is going to be 4. So there's a 400% increase going from 1 to 2, and then from 1 nanometer to 2 nanometers, and there's an 800% increase just going from 1 to 2 here. So I can see volume is going to increase much more quickly. It is 3 dimensions. We're working with 3 dimensions, length times width and height. So I'm going, in this case, length and width and the height. This cube, we're working in 3 dimensions in volume. Where in surface area, we're just working in 2 dimensions. I'm just working on the outside of the sucker. And so this is going to be a whole different ballgame. Volume is going to be going to go very quickly. Let's try to break this down and look at it in a slightly different way. So here I have 2 cubes. Let's say that this cube is for 6 nanometers. This one's going to be 1, so we've got to make it a lot smaller. Let's make this guy a little smaller. I want you to think about surface area as a door. So surface area is analogous to a door. So let's say it's analogous to doors. Let's say doors plural. Now, I want you to think of volume as contents. Think of it that way for a moment. And so let's go back and look at our numbers. You've got the numbers in front of you. So how many doors do I have in this one? So this is in terms of the ratio. Go back and think about the ratio. What does the ratio tell me for surface area? How many doors do I have in that ratio for just 1? And let's ask, I think I picked on Juliana. So Juliana, how many doors do I have? Doors equals Juliana. Did she bounce? No, she's still here. Yeah, Juliana, talking to you, kiddo. You got to give me a chance to help you, and I can't do it unless, oh, can I text me? Thank you. Oh, you're not sure. Well, let's go back and look. Thank you for saying so. It's right up here. So you're looking at your ratio here. So we've got the ratio over here. So doors are going to be on the left, contents on the right. Doors and contents. Let's forget about surface area and let's forget about volume. And let's just think about this as surface area as doors and take that volume and think of it as contents. So how many doors do I have when I'm looking at 1 nanometer? You got it, kid. Excellent. That's 6. Good job. Now let's think about contents. So contents, what are my contents there, kid? How many contents do I have if volume equals contents? And we're still on you, Juliana. We'll go back and look at it. Remember, surface area is doors, volume is contents. We're dealing with this 1 nanometer. If volume is or contents, then what are my contents here? And this is still on you. Yeah, you could think if somebody asks, is it kind of like space, sort of? Yeah, the space inside. You could think of it that way as well. But what is the number that goes there? Okay, 1. Thank you. All right, so I have a situation where I have 6 doors and only, let's pretend this is a person. There's 1 person in here. And if I am 1 person and I've got 6 doors, 6 ways to get in and out of this room, I'll kind of draw it this way. Think of it this way. There's 6 ways to get in and out.
Tipping points are like
6 ways
to
get in and out. It's not going to take me long to get in and out of here, right? So there's very little inside of here. There's just this 1 person. And they've got 6 different ways. So if there was a fire to break out in this room, well, if there's a fire on one side of the room, don't worry about it, I go over here. If there's a fire over here, don't worry about it, I go over here. You can get in and out of this really easily. Well, this is also how diffusion works. Remember the big pot and the little pot? So the little cup of soup. So if you got a little cup of soup, there's 6 doors. If the cup of soup was going to be like 1 nanometer, it'd be like having 6 opportunities or 6 places or 6 doors that the heat could escape that cup. Makes it really simple and easy to get in and out of there. If I have a big pot of soup, I've got a whole different situation. So let's go back to my analogy. So let's go, I don't think I've picked on, let's see, picked on these people. Let's go to another, I haven't picked on Stein. Stein, tell me, doors over here. Doors equals what when we're working at a 6, when we're at 6 nanometers? What are my doors now? And we're using the ratio.
Resilience is positive feedback.
Stein, talking to Stein.
Positive feedback, right? That means positive feedback. It's kind of confusing.
Doors equals what?
Positive feedback is different.
I'm sorry?
It's not.
It would slow that process down a little bit.
Baby, you might, either you have to speak up or you got to put it in the chat. Drop it in the chat. I've got Homo, she's pretty loud. Drop it in the chat real quick. How many doors for this thing? Oh, it's not 6. Let me go back. Let's go back and look. How many doors? We went from 1, now we're over to 6. You're looking at your ratio.
I think we did a good job.
So what are my doors equal to? How many doors do I have? You're looking at your ratio on your table that you made.
Actually, I can.
And I'll go back and let you look at it again. I'm at 6 nanometers.
No.
How many doors are there?
I'm grateful.
And we're stuck on you, kid. How many doors, so to speak? Compare. Okay. There you go. You got it. 1. My contents are still going to be the same. 1. So if this is me and I am a cell, they only have one way for things to get in and out. What would happen if I changed this? What if I got to being 10? What if I changed this and I said, oh, it's no longer 6 nanometers. My doors is going to change to 0.6. So I don't even have an entire door. At that point, I got to get rid of this. I don't even have an entire door. So let me get my eraser. Let's try to get 6/10 of a door. Whew, that's going to be a problem. If you get big, diffusion is going to slow way down. It's an impossibility for it to even probably work well enough. Remember, we're also thinking about diffusion and osmosis. So there's going to be oxygen, carbon dioxide, glucose, all the things that you need to get in and out very, very quickly. Everything that, all those free services stop. So cells would have to work harder and to get what they needed with active transport. It would be so tough for diffusion and osmosis to work that you probably, that cell would die. That cell would not be able to do that. So cells can't grow large, they can grow in number. That's how cells grow. They grow in terms of number. I'm gonna stop sharing this for just a moment. I'm gonna go to our website. What am I saying? Schoology page, so we'll go to 2. I have some independent practice. Now this independent practice I've come to understand does not work well if you're on a Chromebook. So if you're on a Chromebook, you're not going to be able to open this independent practice very well, and at least write on it. You might be able to open it, but you're not going to be able to write on it very well. I'm going to open it, and we're going to look at it together and make sure that you guys can see this. And right now you cannot. I'm going to give you a moment to, you can go get yours, but you see where it came from, I hope. Let's see where you... And this is where I got it. So I was at unit 2. At unit 2, we're still at surface area to volume ratios. I'm not going to get to the osmosis lab just yet. And there's going to be independent practice that you can look at here, but I think probably we're going to have to, I don't know. Maybe I'll give you guys 5 minutes to look it over in a breakout room. You won't be able to write on it, but you can look at it. It's kind of wonky when you open it with in a computer and you use Word, it's easy. So I would recommend opening it in Word if you can, but I just want you to look it over, and then we're going to go over it together. And then I'm going to just miss you guys after showing you what your homework is. But I want you to kind of get the idea. And I'm going to be asking you guys just very detailed questions, and you're going to be answering with the group. So we're going to do it together, but I wanted you guys to give a chance to look it over with your buddies first so that you can kind of talk through it. I'm going to open up these breakout rooms. There's going to be 6 of them, so you'll be in smaller groups. I'll bring you guys back in 5 minutes. Again, you're not going to actually have to do it, but you should be able to walk your way through it with me when we come back. So you have 5 minutes to open the documents and take a look and come back and talk to me.
Why don't we have a guest speaker?
Daniel, you're able to join the room? Javi, are you able to join the room? Javi, are you there? Javi? Hello? Javi?
So what Zoom are you on?
1 through 6.
It's study hall.
Everybody's able to open the document and see it?
Yes.
Yeah.
All right, all right.
Are we supposed to do anything, or are we just?
I don't, the last class, some kids could open the document because they're on a computer and some are on Chromebook. When they open it, the Google Doc, it made it wonky. And it was hard to write on. So I don't think that you could, I'm not going to hold you to it like you have to write on it. But you definitely should be able to work it out. Maybe you would have to write these problems out on paper to practice them yourself. I'm not taking a grade from it. If you don't practice it, you're going to have a hard time when it comes time for the assessment.
Is this how the lab is going to work?
Depends. You can choose your variable. We're going to talk about the lab in about probably 15 minutes.
All right, then.
All right, then. You guys are able to open the document, right?
Yeah.
All right. Yeah, just you just want to be able to. You might have to write these out on paper because the document's hard to write on. If you have a computer and you open it up in Word, it's easy. If not, it's kind of a wonky pain in the butt.
So you just want us to like read over it, right?
Yeah, read over it and be ready to either ask me questions or follow along as I answer them myself.
Okay.
They're not near as hard as you think they are. They're simple. You guys are able to open the document, correct?
Yeah.
Yeah, you're not going to have to write on it. You're not going to have to necessarily write on it, but you should be able to walk through it. So I'm going to, one of you guys is going to be one of the first persons I ask when we come back to help me with some of these. Somebody's asking me to come to another room, so I'm going to bounce, but you guys definitely need to talk. You're the only room I came to and nobody was talking about the document. You guys are going to have to talk about it. You guys are all able to open the document, correct, though?
Yes, we are.
All right, y'all talking through it. Dylan walked out of here. I guess we were TP.
Yeah.
About it.
So we did talk about it, but then we stopped talking about it.
Okay, so did you begin because it was straightforward or it was hard?
Straightforward.
Yeah.
We'll see in a sec. I hope it is.
Oh,
What's up, Eral? Eral.
hey.
Hey. I gotta wait for everybody to get in here and take some 26 seconds for everybody to get out of the room and come back. It'll kick them back in here this time. So Jalen, you're going to be the first contestant on the Pope is Right. So get ready to do it. In about 5 seconds, you're going to help me with the first kind of thought experiment that we're going to have here. Good, we got this out of the way. So in the first, you can see at the top that you're always going to be given a formula. So you'll be given a formula sheet on the exam. You've got the formula for a cube, or if it's a column, or if it's a sphere. It's easy. It's just 4/3 times pi times the radius cubed. Make sure that you're paying attention to that. You definitely want to have a calculator on the next test or the next quiz, which will be next week. But let's take a look at this. We've already done this part, so I always know we already calculated these ratios. let's just think about this question. What's the relationship to size and surface area of a cube? So let me write on this. And let's see, insert, let's draw. So as volume increases, what does surface area do? Does surface area decrease in relation to volume, or does it increase in relation to volume? And that's going to be you, Jalen. So on my y-axis, how do I plot that? Is surface area going to decrease or increase in relation to volume? And you have this right there already calculated because you wrote that down. This is the same thing that we did before we came in here.
It's gonna increase in relation to volume.
How about point? Go like this or this? Because I can't hear you. Is it increase or decrease? So surface area increases like this with volume. That's what you think, yes? Okay. Does anybody disagree with him before we move on? And we're talking about relative to one another. Is this true? Is what he's saying true? Or does somebody disagree with him? I got lots of yeah, I got some yeses and I got some no's. Got some people. Let's go back to let's go back and look at this. Is that true? As I went from small to large, what happened? Did surface area decrease or did volume? I went from 6 to 0.6. Let's go back and look at the previous page. What is happening to surface area? Is it getting smaller or is it getting larger compared to volume? What is happening to volume? Is it decreasing or increasing? And this is an increase in size. So I'm increasing in size from 1 to 10. Surface area, I'm going from 6 to 0.6. I'm going from, but 1 is consistent. We're keeping that the same. Let's go back.
Do we see your screen or no?
I don't think you shared your screen.
Oh, I didn't share my screen. Oh my
Yeah, no, you stopped sharing.
Oh man.
Yeah, that's 5 points.
5 points. Oh
Like
man.
everybody that talks.
Hush. Hush. So here we are again. This is our little analogy. So I'm small and now I'm getting bigger. So I'm going from 1 to 10. I'm getting larger. So I have doors. Remember, doors are surface area. Contents are going to be volume. So as I get larger, what is happening? What's happening to surface area? Let's go back and look at the data. So here I am. I'm getting larger. This is getting larger. So my length is one side is getting larger. Here I go from 6 to 3 to 2 to 1.5 to 1.2 to 1 to 0.9 to 0.8, 0.7, 0.6. But my volume is staying relatively, obviously it's getting larger. I could see that. Obviously volume is going to be increasing, but relatively speaking, comparatively compared to these two, is surface area actually increasing or decreasing? That's the question that we're asking. As they get larger, what's happening with that ratio? Is it increasing or decreasing that ratio? So let's go back to our document that we're using. So do we agree with Jalen still?
So I actually have a question. I think like why, if we see on the surface area that it's increasing, so then why is the ratio different, or is that just the math?
It's just, well, it's the ratio is changing. They're both obviously they're both going to increase. We're talking about in relation to one another, and that's what I'm thinking in terms of the ratio here. So the ratio, surface area is going to go down. I'm not working on these 3 dimensions that I'm working with volume. As I get big, and think of it this way, sweetheart. So if you're a baby, if I take an infant, Now, this is going to sound terrible. I take a 1-day-old infant. They probably weigh about 2 kilos. Little bitty baby, 2 kilos, about 6 pounds or 4 or 5.5 pounds. And I stick them out in the snow. You're going to be like a hateful person. I stick that naked baby out in the snow. And then I take a naked, full-grown person, and I stick them out in the snow. We've got heat that's leaving our body. Which one's going to freeze faster? The baby or the adult?
The baby.
Baby, you guys instinctively understand this whole health thing, and it's because the baby is small, so their surface area to volume ratio is super high compared to an adult. I'm bigger. I have fewer doors compared to my volume, so the baby is going to freeze really, really quick. If you have a drop of water and you put it in the freezer, and you put a glass of water in the freezer, which one's going to freeze more quickly, the drop or the glass of water?
Drop.
The drop. It's got a ton of surface area compared to its volume, a ton of it. And so what's the relationship to that size? Well, as volume increases, ratio of surface area is going to decrease. You have to kind of keep that in your back pocket as you think about that. So when you're looking at this scenario, and this will be the last one that I do before I go and I deal with telling you what you have to do for the lab. So when we're calculating, let's just calculate this real quick. So 30 times 30 times 30, that's going to be my volume. Let me change this and get back to writing. I don't want to draw anymore. I just want to write. I just want to write. Can I draw it? Yes, I should be able to write. Okay. So what about this one? This is, how many cells do we have here? How many cells do you guys see? This is 1. Well, how many cells are here?
27.
27, that's right. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 3 rows deep. So I've got 3 times 9 is 27. Well, what changed? Did volume or surface area change in these two? Well, let's see. So I feel like the volume, let's just calculate this. So this is the formula for volume is going to be length times width times height, and surface area is going to be length times width times 6. So what is 30 times 30? 30 times 30 is
900.
And times 6 is going to be
5,400.
Okay, this is going to be 5,400. So my surface area is 5,400. Wow. Okay, let's do volume. So 30 times 30 times 30. What is that?
20.
I'm sorry?
27,000.
7,000. Okay. Let's go over here. So let's just calculate one of these and then multiply it times 27 to get my total surface area. So we're going to calculate surface area over here. So let me tab over here. And I'll ask somebody for that. So let's see. My next contestant is going to be, I don't think I've picked on, oh, I haven't picked on Aspen. So Aspen, what is 10 times 10?
100.
100, okay. Now we're doing surface area, so we've got 100, that's going to be times 6. So that's going to be 600. 600 times 27, what is that?
Let me do
Actually, hold on a second. We're doing surface area. So, yeah, it's 100 times 100 times 6. Yeah, 600 and then times 27. What is that?
16,200.
16,200? Roger that. Now, let's see this volume. Is a volume the same for these? So all we're doing for volume is just doing 100 times 100 times, or excuse me, 10 times 10 times 10, and that is going to be what? 10 times 10
Oh my God, I hit you the last time on the Zoom. Let me see.
100 times 10 is going to be?
That's the most awkward feeling.
Yeah, I'm sticking on Aspen. So, okay, so if this is 1,000 times 27 is going to be
2,700.
1,000 times 27.
Oh, how many?
27 times 1,000.
Oh, 27,000.
27,000, yeah, 27,000. So now my volume stayed the same. I increased my surface area. So if cells get really small, they're going to be able to increase the rate of osmosis and diffusion and all those free services. All right, last, I'm just curious about this one really quick. When you look at this, I just want to know which one has the greatest surface area to volume ratio, A, B, C, or D, without doing any of the math. There's no reason to do math. Which of these, if you were given this question, would you answer in a heartbeat and say, it's this? Let's see what you guys get. Go for it. And just drop it in there. Do it not to everybody. Just give it private. Private. Keep it private.
What do you
Which one has the greatest surface area to volume ratio? Do not listen to Earl. I don't know what Earl's thinking. Or Cam.
You said which one has the greatest
surface area to volume ratio. Yes. Which one's going to be most efficient? Which one is going to be most efficient? Is it more efficient to be small or more efficient to be large? That's essentially the question. Good. Keep it up. 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 Cam, you've got to start sending me stuff privately. You're just broadcasting your ideas out there to everyone. Everybody can see your answer. I'm trying to find out. Somebody could steal it. All right. It looks like, yes, most of you guys are saying A, and that's right. There's no reason to sit around and do the math here. You can just look at this and go, if you're small, diffusion and osmosis can happen really rapid. Now let me stop sharing my screen, go back to the website, and tell you what you have to do. Now, when we come back, I want to be really cool with you guys. I want to be very cool with you guys. So I have attached a demo. Now there's 3 variables that you can use. I have attached a demo lab. This is me doing the lab. It's only 15 minutes. I'm using surface area to volume ratios. So if I click on it, and gotta listen to myself, I sound like a moron. This is something that you're going to actually do at home. I'm not going to give you my data. You have to actually do this at home. You'll see how easy it is. These are potatoes. You do not have to use surface area to volume ratios as your independent variable. What are other variables that we could use to test osmosis? And I just want to know 2 before we leave, and then that's it. That's your exit ticket. What are 2 other variables that could be used other than surface area to volume? Other than surface area to volume. I realize you can't see that. This is the lab. What are 2 other variables that you could use? This is me. You can tell it's a 15-minute video. You're going to watch the video, and then I'm going to come back and answer any questions that you have. I'm going to spend all the time answering all the questions that you have. But what are 2 other variables that you could use other than surface area to volume ratios? Yes, to test the rate of osmosis. Okay, good. I've got 1 person. I'll tell you in a second, but I need everybody to take a stab. Ooh, Abby, you got 1 of the 2. Abby, you got 1 of the 2. You got 1 of the 2. What are the other ones? Technically, Precious, you're right, but we're not going to use that one. Okay, cool. Mock, you've got another one. You need to formalize, there's a term for that. So I've got Abby and Mock and Precious that both give me technically variables that we could use. Give it to me private. What's the other variable? What are other variables that we could use to test the rate of osmosis? Yeah, Precious, that's possible, but we're not going to, yeah. That if we applied force to it. Yes, and for diffusion and osmosis. What are the other variables? Let's go. I'm going to share my screen again. I'm going to go back to my do now. My do now.
Wait, I'm confused. So you said
So this is a variable. This is an experiment. Am I right or wrong?
Yeah.
Yes. The surface area to volume ratio is the same for every one of those. So that's a constant. What's the variable here?
Yeah, that's why she's doing that Jew thing. Her boyfriend, he's just really.
What's the variable that they're using?
That's how I found out about the podcast. Somebody posted a clip like.
Oh, we got lots of answers now.
He's a normal person. They've been dating for 6 months, about to.
Okay, concentration gradient. Yes, finally one of you guys said it. Solution amounts. The solution amount is the same. The concentration gradient is different. The concentration gradient is going to be different. Volume is the same. All right, watch this video. Don't come in half-cocked, and I will help you through that to make it easier. But make sure that you have watched it and you have a list of questions for me so that we can do this together on Tuesday.
So she's on this guy's podcast.
Deuces,
right?
kids. Deuces.
And then after that, they did this thing 7 months where like they did the batch. And I think he was one of the contestants.